Hi, Dr. Terry Williams, I'm CTO at Filtronic, and today we're going to be talking a bit about power amplifiers, particularly the high power amplifier that's used in a comms system, in a communications-based system, to boost the power before we start transmitting data via the antenna. So there's really two different types of power amplifier. There's a travelling wave tube amplifier, so that's a vacuum type device, and then there's a solid state power amplifier which comes from underlying semiconductor technology. So the tube amplifier is quite a complicated device. It's tube based, as I say, very hard to manufacture, quite complicated, but it's been around for many years and there's still an incumbent solution in many of the applications. The solid state alternative comes from very small semiconductor devices, which then can be combined to make higher power devices to start to compete versus the TWTA. And they both have some benefits and some challenges depending on what application you're trying to look for. Travelling wave tubes are particularly good when we get to very high power applications, and frankly they've displaced the SSPA, and they're the incumbent technology really for low power applications. So at lower frequencies, if you want really very high power, kilowatts of power, then the travelling wave tube solution is the right one. As we push up in frequency, again there's some benefits as we push to really high powers, but the SSPA is really starting to displace at the lower power levels and starting to get higher in power levels as we push up the power of new semiconductor devices. And that's driven by new sort of compound semiconductor devices. As we start to get increased power density, we can start to use SSPAs to displace this incumbent TWTA technology. And the real benefit of that is cost and performance. So as I said before, these travelling wave tube devices are very complicated to manufacture. They take a long time to make. They're very hard to scale to volume, whereas the compound semiconductor devices can be made in mass volume and produced on production lines that can produce very high volumes of devices. So when we talk about scaling these SSPAs, these solid state power amplifiers, to higher power levels at higher frequency, this is where Filtronic are really taking the lead. I'll be talking a little bit later on in the presentation about the things we've done to improve that and to get really state-of-the-art and leading-edge performance for these solid-state power amplifiers. So then moving on to some of the pros and cons of the two technologies, TWTAs and SSPAs. In terms of the TWTA, as I said, they can reach higher powers. If you want very high powers, then the TWTA is the optimum solution. They also have very high efficiency. So if efficiency is important to your application and trying to keep that cost of ownership down, that can be one benefit of TWTs. But they do have quite a big drawback in limited lifetime and lifespan of the device. So typically a TWTA will operate somewhere between 50,000 and 100,000 hours, and that would compare for equivalent SSPA to about 1 million hours of lifetime. So obviously quite a big difference in that lifespan. So if you have a long lifespan application, then SSPAs have a big benefit there. So then moving on to the SSPA and some of its pros and cons. It's starting to increase in power. As I said, the very high power levels are still better served with TWTs, but we're starting to see, and I say Filtronic is driving the progress here, particularly at millimeter wave frequencies, this increasing power of SSPA, which is starting to displace quite rapidly the TWTAs because of the benefits. And the big benefits we have are lower cost. They're much easier to produce, much easier to manufacture. That brings down the cost of ownership right down for the original module. They're also a very long lifespan. As I said before, the TWTAs can have a limited lifespan, 50 to 100,000 hours, whereas SSPAs operate for up to 1 million hours. That's really important on systems like geosatellite systems, where you want a long lifespan for the satellite, 15 years. You need these things to last. And again, in things like defense applications where you have a long lifespan, you need coherent operation. SSPAs are really leading the way in that long lifespan and high performance category. So in terms of the SSPA, one of the final frontiers really is looking at space, which is a really interesting market and a real big growing market for Filtronic. Here we see things like the uplink, so the ground side needing very high powers at typically very high frequencies. As we push the capabilities of satellites, things like Starlink and SpaceX have these communication satellites. They need very, very big data links between ground and the satellite to serve all the users below. That leads to a much increased frequency, range of operation, and obviously you need the power to boost that from ground to satellite. And this is really where Filtronic are pushing the boundaries. We're working at very high frequencies at the moment, up to 86 gigahertz, so 81 to 86 gigahertz at E-band. And we're pushing the frontier there and pushing technology through proprietary techniques such as amplifier combining, which I'll come back to in a later slide. So I talked about us improving the performance of these solid-state power amplifiers. And what's really driving that is the underlying semiconductor technology. We've moved away from single-element solutions like silicon to compound semi solutions like gallium arsenide and gallium nitride. These give massive improvements in power density and high frequency of operation that allows us to start to really push the power levels at these very high frequencies we talked about, so up to 86 gigahertz, with new technology that underlines that. So now we have the underlying semiconductor technology, which is pushing the frequency and the power levels to the right sort of power levels. The next thing we have to do to reach the very high power levels, for example, for the ground systems of these space applications, is to combine multiple devices into a single amplifier. So that's really important. Each amplifier will only give us maybe half a watt to 2 watts per amplifier. So at Filtronic we've developed proprietary technology. It's an ultra-low loss waveguide combiner that can combine multiple devices into a single output. And we're actually doing that with up to 32 devices. So we have 32 MMICs, all combined into a single output with very low loss, which gives us really, really good performance. It's cutting edge. So that 81 to 86 gigahertz band at the moment, using gallium arsenide MMICs, we're getting about 20 watts of output power, which is world-beating performance. Some of the things we need to do to achieve that is we design the underlying technology, so we do our own MMICs at Filtronic. So we design our own MMICs, and that means we can get the best possible technology for our application. We can design specifically to a particular application, but it also gives us benefits when we start talking about that combining, the combining stuff. When we combine these multiple devices together, it's really important that each set of devices has very similar performance, particularly in terms of phase and magnitude. So we have to pre-screen these devices to make sure we get the optimum combine. And to do that, if you have your own wafers, you can pick from similar parts of the wafer pattern and actually get very similar performance without having to search many devices to find similar devices. So it really cuts down the cost of ownership. And also in terms of cost, back to that point with cost, if we have our own underlying device technology, that means we can drive down the cost without having to buy off-the-shelf commercial parts. So what does it give us when we have this amplifier, this high-power solid-state amplifier? It gives us massive reliability improvements over the tube-based amplifiers because it's solid-state itself. But also, because we're combining multiple devices, if we have one device fail within a system, the rest, the 31 other devices will still operate and give you most of the power. So you won't actually have a single point of failure. We get multiple points of failure, and that means we can run for longer, less chance of anything going down, and better performance. So that repeatability between amplifiers as well, so we can talk about multiple amplifiers all having very similar performance. The manufacturing is high volume, it's highly repeatable, unlike tubes where you have to tune performance, and they can be quite different actually from tube to tube. So given all the benefits we talked about with solid-state power amplifiers, what we're seeing is the adoption of these, as I say, from low frequency now right through to high frequency in a range of different applications. That could be anything from communications. We talked about satellite already, that's starting to grow and a really important part for Filtronic. But also in defence, we're seeing a similar thing where Filtronic are now displacing TWTs in many defence applications where that was the incumbent technology. So moving on to the application side, one of the big applications that's been driving a lot of business through Filtronic are mega constellations. So these are things like SpaceX's Starlink constellation, which has thousands of satellites already. People like Amazon also joining the fray, and OneWeb, all with lots and lots of satellites in the air, really changing the whole dynamic of the space industry actually. What we've seen in space originally is big geosatellites, massive satellites, take years to build, stay in service for a very long time. And we've moved away from that now to low Earth orbit satellites, which only have a very short lifetime, maybe 5 to 7 years. but have lots of capability, and there's lots of them. So what's required behind that then is a massive reduction in cost. We can't sustain the sort of price point we had before for big geosatellites. We have to really cut the cost. And these constellations are really important for society, really. They're helping to deliver, for example, the next 5G systems, and starting to merge those non-terrestrial networks into terrestrial networks, which gives us connectivity everywhere. So instead of people being connected only in certain places in the world, everybody starts to be connected. So this is really important for driving down inequality. So developing countries where we have poor connectivity now have connectivity that they didn't have before. But even in developed countries like America, we see big swathes of the country who are currently unconnected, and we're trying to break that digital divide, both in the UK and in other countries across the world. So as I said before, the cost now becomes really, really important, a really significant factor. If you think about having to equip, for example, in the Starlink constellation, 50,000 satellites, the cost has to dramatically fall from where we were before. We have to get devices that are scaled at volume, and that's really plays into Filtronic's strengths. Our traditional background is in the telecoms market, where we're developing very high volume telecoms products, mainly at the backhaul side, so moving large amounts of data from point to point on the ground. And we're starting to reapply that technology now from ground to space and from space to ground to produce really high quality, very high frequency, high data rate devices that are much lower cost point, which are repeatable, they have high quality and reliable performance like we talked about before, that SSPA now driving that reliability up away from where we had that TWT performance. And the ability, as we said, to scale at massive volume. And we do all that from the UK in our manufacturing facility in Sedgefield in County Durham. So we've seen over time that SSPAs already have actually displaced TWTs at lower frequencies. So what we've seen in the space applications in particular is that lower frequencies up to about Ka band solid state solutions on the ground start to displace the TWT because of all the benefits we talked about already. Where Filtronic had the real values above that frequency, so looking at Ka band and above, at frequencies like Q and V band, at E band, where we have underlying technology, underlying developed technology from telecoms that we can actually reuse for satellite. For some examples of that, we've recently undertaken. We're undertaking some design work for a payload application. Those are at Ka band and QV band. And again, applying our technology, our high volume processes, our advanced manufacturing facilities to produce very high quality, high volume, low cost modules for space. On the ground side, we've seen applications at even higher frequencies, so working with one of the big satellite constellation providers to produce really high power devices, so up to 20 watts in gallium arsenide, these combined devices we talked about before, for the ground station side to produce a big data link with 5 gigahertz of bandwidth at E-band, 81 to 86 gigahertz. So talking about what's next, really it's the semiconductors that hold the key, so the underlying technology. I've talked about that E-band amplifier for a start. So in gallium arsenide at the moment, so combining those 32 devices gives about 20 watts of output power. If we can move that to GaN, so gallium nitride technology, and we're starting to see those processes really start to open up now, and the node size dropping down. We're seeing processes as low as 90 nanometers, which will support frequencies up to 100 gigahertz. So we can start to do those E-band amplifiers, and we have design projects underway at Filtronic to do that. And we'd expect then to get powers at E-band to 81 to 86 gigahertz, maybe up to 60 or 70 watts, which is the next generations of demand for those sort of frequency land. So I talked today about solid-state power amplifiers and how they're starting to really displace the TWTAs, particularly these higher millimeter frequencies driven by some of the technology we developed at Filtronic. And it's really our core expertise, as I say, our telecoms background at these very high frequencies, our advanced manufacturing capabilities, our process development teams, and our design teams that have 10 years plus experience at these very high frequencies that have really driven that. And that combined with these advanced combining technologies I talked about before, our sort of state-of-the-art combining networks in waveguide that have very, very low loss and let us get to these scale to these very, very high powers, are really starting to lead the market in that area. So if you have needs for SATCOMs or for defence at these very high powers, particularly in the millimeter wave frequency ranges, then come and talk to Filtronic.